Alright team, welcome back to the channel. If you're building with AI today, you've undoubtedly been bombarded by terms like vector databases, RAG apps, and BAI, low-latency enterprise AI. It's easy to feel like you're drowning in a sea of acronyms and buzzwords, isn't it? There's so much hype, so much noise, that the actual signal, the critical information you need to build robust, performant AI solutions, often gets lost. You might be wondering if this is just another fleeting trend, or genuinely a foundational shift. And frankly, the confusion is rampant, even among seasoned engineers. Think of it this way. Building effective AI systems without understanding vector databases is like trying to construct a complex skyscraper without first laying a clear foundational blueprint for its core structure. You might get something up, but it won't be stable, scalable, or secure. I've seen teams invest months, even years, struggling with lagging adoption of advanced AI technologies, attempting complex migrations, or trying to fine-tune massive LLMs for niche markets using inadequate infrastructure. They often face data scarcity, quality issues, and severe hardware constraints, all because their data layer isn't optimized for the unique demands of semantic search. This isn't just a developer concern. It becomes a major headache for PMs trying to scope roadmaps, security teams grappling with new attack surfaces, and operations struggling with cost and performance at scale. It underscores a demand for robust technical solutions that go beyond AI slop or hype.
The core challenge is integrating domain-specific data efficiently. So before we dive deep into what vector databases are and how they work, let's acknowledge this initial confusion, because recognizing where we're lost is the first step to finding clarity and truly understanding why this technology is becoming an indispensable component in today's enterprise AI stack.
Last scene, we navigated the hype. Now let's demystify vector databases, starting with their core, vector embeddings. An embedding is AI's language for context. It transforms complex data, text, images, code, into a numerical vector representing its meanings. Similar meanings map closer in high-dimensional space, giving AI fundamental comprehension.
You might wonder, can a regular database handle this efficiently?
The answer is no. Traditional databases excel at exact matches. But for semantically similar items, for understanding meaning, they fall short. They lack specialized indexing for high-dimensional vectors, leading to painfully slow performance. It's the wrong tool for this job.
This is precisely where vector databases shine. They are purpose-built, storing high-dimensional vectors and enabling lightning-fast similarity searches. Imagine a library finding books by theme. Using clever approximate nearest neighbor (ANN) algorithms, they efficiently locate semantically closest vectors, even among billions. This specialized architecture is fundamental for intelligent applications. For RAG applications, vector databases are imperative. Picture an enterprise LLM hallucinating incorrect financial data to a client without one. I've seen teams struggle for trustworthy AI with proprietary info. Vector databases empower RAG to fetch real-time, relevant context, slashing hallucinations. This isn't just technical. For product management, it builds accurate AI features that delight users. Low-latency enterprise AI demands optimization. Vector databases use advanced indexing, like HNSW, for speed and scalability. They support sharding and distributed architectures, spreading massive datasets. This keeps AI applications responsive. For operations teams, this means stable, high-performing systems, minimizing costly downtime. Beyond RAG, vector databases unlock diverse AI. They're crucial for recommendation engines, helping users find products. They power anomaly detection, flagging unusual activity. They simplify deduplication. This broadens horizons for business stakeholders, revealing new avenues for innovation and competitive advantage. Ultimately, understanding vector databases is like grasping the foundational blueprint for mastering modern enterprise AI. They're not just a feature, but a core data layer for advanced AI applications.
By providing scalable, efficient semantic search, they pave the way for seamless, intelligent AI integration. But how does this truly transform cross-functional AI initiatives? We'll explore that next. So far, we've broken down what vector databases are and why they're crucial for RAG. But their influence extends far beyond just the immediate technical implementation. Think of them as a central hub, a crucial component in the foundational blueprint for understanding and mastering modern AI strategy across your entire organizations. For developers, this means moving beyond manual data retrieval. You gain the ability to build sophisticated, context-aware RAG applications with far less boilerplate code. You might be thinking, does this just add another database to manage? Not really. It abstracts complexity, letting you focus on feature delivery instead of complex semantic search logic. This isn't just a developer concern. It directly impacts a product manager's roadmap by enabling richer, more intelligent features that users actually value,
accelerating your innovation cycles.
Data scientists and ML engineers benefit immensely too. Customizing LLMs for niche markets often faces hurdles like data scarcity and quality. Vector databases allow you to curate and retrieve high-quality, domain-specific context effortlessly, enhancing model performance without expensive fine-tuning or specialized hardware. It's about feeding your models the right information at the right time, making your AI more accurate and less prone to hallucinations. In real systems, this shows up when operations teams face the challenge of scaling AI infrastructure. I've seen teams struggle with traditional databases, trying to handle billions of vector embeddings, leading to performance bottlenecks and soaring costs. Vector databases are purpose-built for this scale, ensuring the low latency critical for real-time RAG applications. This translates directly to a smoother user experience, reducing the load on your existing infrastructure, and ultimately, driving down operational expenses for your DevOps and cloud teams. Then there's the critical aspect of security and compliance. With sensitive enterprise data flowing through RAG systems, managing who has access to what, and ensuring data privacy is paramount. Vector databases, when designed correctly, offer granular access control, data encryption, and audit trails for your embeddings, making it easier to meet regulatory requirements and protect proprietary information. This peace of mind is invaluable for any security and legal department navigating the complexities of AI governance. Ultimately, for business leaders and strategists, vector databases aren't just a technical detail. They're an enabler for innovation. They unlock the potential for new, intelligent product lines, improve customer service through more accurate AI assistance, and accelerate data-driven decision-making. This strategic advantage allows your company to differentiate itself in a competitive landscape, bringing tangible ROI much faster. Across the enterprise, from building innovative apps to securing sensitive data, managing scalable infrastructure, and driving strategic growth, vector databases play a foundational role. They empower every part of the organization to leverage AI effectively, moving us toward a more unified and intelligent future. But how do we actually implement this effectively? Mastering the techniques like indexing and sharding. Let's dive into that next. For low-latency RAG apps, simply storing vector embeddings isn't enough. Imagine searching a massive library without a catalog. It's slow, inefficient brute force. We need intelligent retrieval. This is why vector indexing is crucial, forming a core part of the foundational blueprint for understanding efficient vector search. It quickly narrows down relevant results. Data engineers must design ETL pipelines with indexing in mind to prevent bottlenecks, impacting the entire data flows. Vector indexing uses approximate nearest neighbor (ANN) search, creating a clever map of your vector space. Algorithms like IVF-flat and HNSW offer different trade-offs. IVF-flat groups vectors into clusters for focused search, while HNSW builds a multi-layer graph for rapid traversal. Choosing between them means balancing speed, accuracy, and memory. This decision isn't just technical. It directly impacts operations teams, cloud infrastructure costs, and product managers' ability to deliver features with specific performance (SLAs). But what if your index data still overwhelms a single machine? This is a common bottleneck for large enterprise datasets. Picture a single powerful server buckling under billions of vectors and thousands of concurrent queries.
Sharding is the answer.
It breaks your dataset into smaller, manageable chunks, distributing them across multiple servers. Each shard operates independently, enabling horizontal scalability. I've seen teams struggle without early sharding plans, leading to costly, complex migrations. This distributed architecture also presents critical considerations for security teams managing data locality and compliance. When combining robust vector indexing with intelligent sharding, you unlock true low-latency performance for RAG. Indexing makes each shard lightning-fast to search, while sharding ensures your system can handle massive data growth and query volumes. A query is routed to the right shards, where the index quickly finds relevant results.
This synergy delivers near real-time AI responses, even with petabytes of data. For business stakeholders, this translates directly into a more responsive, intelligent product and faster, more reliable insights. So what are the actionable takeaways? Understand your data. Choose indexing algorithms wisely based on latency and accuracy. And plan your sharding strategy early for future scale. Continuously monitor, iterate on parameters, and anticipate dynamic resharding. Mastering these strategies ensures your RAG apps are performant and scalable, not just functional. It's about continuous optimization. Next, we'll dive into measuring that impact, how to evaluate the ROI of your vector database, and emerging trends.
Now, as we near the end of our journey, let's talk about the end game: future-proofing. It's not enough to just adopt vector databases. We need to prove their value and understand where the technology is headed. Measuring ROI for your RAG applications isn't just about technical performance. It's about quantifiable business impact. So how do you actually measure this? We're looking at metrics like reduced hallucination rates, meaning fewer incorrect AI responses, faster query response times for users, and improved accuracy in information retrieval. These directly translate into better user satisfaction and, importantly, reduced operational costs associated with fact-checking or error corrections. And this isn't just a concern for developers or data scientists. It significantly impacts product managers, who see direct improvements in user engagement, and even legal or compliance teams, who benefit from the provable reduction in misleading AI outputs. Proving this value is key to securing continued investment. Looking ahead, one major trend is the rise of hybrid databases. Instead of separate systems, we're seeing databases that seamlessly integrate traditional, relational, document, and vector capabilities. This simplifies architecture and reduces data synchronization overhead, making the foundational blueprint for understanding and mastering your data infrastructure much cleaner. I've seen teams struggle with managing disparate data stores for years. Picture a moment where a single database could handle both your customers' structured profile data and their unstructured query embeddings, all with low latency. This integrated approach drastically cuts down on architectural complexity and speeds up feature development cycles. Another significant development is in advanced indexing and search techniques. Beyond HNSW, new algorithms are emerging, alongside techniques like quantization and specialized hardware acceleration. These innovations promise even faster, more memory-efficient vector search, enabling RAG applications to scale to unprecedented levels without compromising performance.
We're also seeing vector databases play a larger role in semantic caching and knowledge graphs. By using vector embeddings, systems can intelligently cache semantically similar queries, reducing redundant LLM calls. Integrating with knowledge graphs creates richer, context-aware RAG, pushing AI beyond simple keyword matching towards true conceptual understanding. Ultimately, mastering these trends means building an adaptable, resilient AI landscape. It's about ensuring your RAG applications aren't just powerful today, but remain at the cutting edge for years to come, consistently delivering intelligent experiences and significant business value. Thank you for joining me on this deep dive into vector databases. If you found this insightful, please hit that like button. Let me know in the comments. What's your biggest takeaway? Or what challenge are you currently facing with RAG? And don't forget to subscribe and hit the bell for more in-depth tech explainers. You can grab the full playbook and resources for this topic via the link in the description below.